Hey everybody, so this video is going to cover analyzing rate functions. So we talked before about analyzing particle motion, and so we looked a lot at velocity and acceleration. Velocity is only one of the rates that we can actually deal with when we're looking at AP calculus problems. So this lesson is going to dive into other types of rate functions. So if you take a look, we've got two learning targets. I can interpret the meaning of a definite integral in accumulation problems, and I can determine the net change using definite integrals in applied contexts. So this first one is going to be a big deal. I can interpret the meaning. We've done that before. We're just going to do it in different contexts now. And then the second part is determining net change using definite integrals. These applied contexts are all going to deal with different types of rates. So this first part here is really important for you guys to recognize the velocity of a particle is not the only rate we can use to analyze a scenario. We can apply the same concepts that we use to analyze particle motion to applied rates problems in other contexts. So let's see what this actually means. Let's do a quick review of interpreting integrals and look at some other rates that we've even talked about already. So S of t represents the rate at which snow is falling on a driveway in inches per hour. So that's a different type of rate already, right? That's not a velocity function, but it is a rate. So snow is falling on the driveway at this rate S of t. Explain the meaning of the integral from 2 to 7 of S of t dt using correct units in the context of the problem. So the integral from 2 to 7 of S of t dt represents. And remember, you need three things in all of your interpretations. You need the noun or the thing that you're talking about, you need units, and then you need the time that you're talking about. So for this one, since S of t is the rate at which snow is falling on the driveway, then if we do the integral, it represents the amount of snow that fell on the driveway. It's got to be measured in inches. And then this is over the interval. T equals 2 to t equals 7 hours. Remember, anytime we're struggling, if we need to look at what the units are to help us out, that can work too. So we know that for this integral, we would be taking inches per hour and multiplying by hours, because when we're doing an integral, we know that it's the height of the function, so whatever the integral, or I'm sorry, whatever the units are for S of t, which is inches per hour, times the x-axis, which would be in hours, and so we would end up getting inches. All right, and we covered that a lot in, I think, Unit 7. I think it was Unit 7, maybe 6. So we can always talk a little bit more about that if we need to, but we did do it before. Let's do one more. R of t represents the rate at which water is filling a tank in gallons per minute. So explain the meaning of the integral from 0 to 9 of R of t dt. So 0 to 9 of R of t dt represents. So if this is the rate at which water is filling a tank in gallons per minute, then the integral must actually be the amount of water that went into the tank. So represents the amount of water that went in the tank measured in gallons. There's our units. And then over the interval. T equals 0 to t equals 9. And we're talking about minutes here. All right, so again, it's those three things. What is the thing? It's the amount of water that went in the tank. How are you measuring it? In gallons. And then what's the time? It's the interval from 0 to 9 minutes. All right, so we've done that before. So now let's look at a sample problem that might actually be from an AP question. So the rate at which people enter an amusement park on any given day is modeled by the function e, defined by this right here. I'm not going to read it out loud to you, but there's our function e. The rate at which people leave the same amusement park on the same day is modeled by the function L, which is defined by this function. Both E of t and L of t are measured in people per hour, and time t is measured in hours after midnight. So that's going to be important. E of t and L of t are measured in people per hour. Time is measured in hours after midnight. The functions are valid from 9 to 23. So if we think about that, time is hours after midnight, so that must mean they open at 9 a.m. and that they close at about 11 p.m., which would make sense. So that's the hours at which the park is open. At time t equals 9, there are 10 people in the park. So this really gave us, I underlined 4 key pieces of information. We're going to talk mainly about 3 of them. But you can tell that this is a rate functions problem because you're given equations for 2 different rates. So the first one that we're given an equation for is this E of t, which is the rate at which stuff, whatever it is that we're actually measuring in the problem, so the rate at which stuff is coming in. And so I always like to label that one as rate in. So E of t is the rate at which the stuff is coming in. In this case, we're talking about people. And then if we look, the second thing that we're given usually in these problems is an equation for the rate at which stuff is going out. So in this case, that's this L of t. People are leaving the amusement park. They're going out of it. And then I underlined the units because those are always going to be important when we're analyzing things. That's not something we're going to put in this box down here, but the units are always important to pay attention to. The last really important thing that we usually get in these problems, though, is the initial condition. Or the initial amount of stuff, depending on the problem. So in this case, we were given that at the opening, there are 10 people in the park already. So these are really the 3 things that you can always expect when you're given a problem where you're going to have to analyze the rate functions. All right, so for the next page, I'm flipping out of the book and onto some paper instead. Sorry.